All right, in the second part of this chapter, we are going to now cover 3-point mapping. And so the purpose of this is determine the order and the distance of 3 genes on the same chromosome. So how do we do 3-point mapping? There's 3 criteria. So the parent, the individual we're looking at must be heterozygous for all 3 genes under consideration. The phenotypic class must reflect the genotype of the gametes of the parents, and then a sufficient number of offspring must be produced for a representative sample. So this probably doesn't make much sense right now. So this is kind of an example of what we mean. So we have a heterozygote individual, PRVBM. So we're now dealing with Drosophila allele names. So plus means the wild type. This is the mutant allele. And so we have 3 genes, and they can either have the wild type allele or the mutant allele. In this situation, the plus is dominant. So this allele is always dominant to the other allele. And so we have a heterozygote that we cross, and this is simply a test cross. So we cross to individuals that have recessive of all. So these 3 genes are all on the same chromosome, but we don't know how far away they are. And further, we don't know the position of them with respect to each other. So which gene is first, which gene is second, and which gene is third. And so our goal is to look at a large number of offspring from this cross in order to determine 1, the order, and then 2, the distance. So how far apart they are. And again, we mean genetic distance. All right, so first, this figure nicely illustrates kind of the possibilities that we were thinking about. So is the V first, PR second, and BM third? Another situation might be the V is first, but the BM is in the middle, and PR is the last one. Or perhaps V is not the first position, it's in the second position. So there's a large number of different possibilities that can occur. The other thing you have to worry about is what is the parental gamete combination. So this situation shows you when V is first, PR is second, BM is third. And this one right here, so these 2 situations look at, both the order is the same. So V, then PR, then BM. So what is different about these 2 situations? So in the first case, this shows that the linkage of the plus allele is to the 2 mutant alleles. So for PR, the plus allele is linked to the 2 mutant, and the mutant of PR is linked to the 2 wild type alleles of the other genes. Whereas in this situation, the wild type alleles are all linked together, and the mutant alleles are all linked together. And so this cross will also tell us the parental combination as well. So really there's a third thing that we're also often interested in, and that is what is the parental gametes, for this individual right here. And so we perform this cross, and so there are a number of possible phenotypes that can arise from this cross. So this is shown in the first right here. Okay. And so this individual simply is wild type here, and then it has the mutant for this and this. This one is the mutant for the first, and then wild type for the other 2. And we count how many of the animals actually have this. So 230 have this phenotype, 237 have this. 82 have this phenotype, 79 have this. 200 have this, 195 have this. 44 and 42. So again, note we don't know the order of these 3 genes. We're just simply listing the phenotypes of this class. So what is the genotype of this individual? So the genotype of this individual must be this. Because again, we know that this individual has supplied 1 mutant allele of each, and then this individual right here must have supplied a plus VBM in order for the offspring to have this phenotype. So it has 1 dominant allele, so it's wild type, and then it has the recessive phenotype, so it must be homozygous recessive for that. And so this, for example, would be the gamete that is supplied by this. So we look at these numbers, and one of the things you'll notice is that they've been grouped together already. And so how is this grouping done? So the way this grouping is done is by looking at the numbers. And the idea is that there are 4 different categories. So one of the and each category has a different expected number. So one of the categories is the most common. So you can see that 2 of these have 230, 237. And so these are the 2 gametes that have the most. And so that is why they are grouped together. They're the 2 that have the most. Then we group the 2 that have the second most together. Then we group the 3 that have the third most together. And then we group the 2 that have the least amount together. And so why are there different numbers? So these are the parental gametes right here, and the parental gametes are the most commonly found. And so we saw this, for example, in the double crossovers, the parental gametes are always the most common. And this is also true now with the 3-point mapping. So when we look at the alleles that are produced, this is the most common the most common are the parentals. You also have 2 single crossovers. So these are gametes that are caused by single crossovers that occurred between the genes. And there's 2 different categories of those. The last category is the double crossovers, and the double crossovers are the least likely to be found. So, 44 and 42. So these are the least likely, and this is how we assign these to the double crossovers. So what are the double crossovers? So again, just a reminder, the double crossovers occur when this situation occurs. So you have a cross that occurs, one of the crosses occurs between the first 2 genes, and the other occurs between the second 2 genes. And as a result, you've actually flipped the middle allele so that it is opposite of the original combination. So now from this data, we can start to exclude certain possibilities. So we know that this possibility right now is not true because the parental gametes we know are plus VBM and then PR plus. So we use the phenotypes in order to infer what the gametes were from this individual. And so we can figure out what the parental gamete combination is. So plus VBM. So plus VBM. So this one is still a possibility. Plus VBM. Nope, this is not a possibility. Plus VBM. Nope. Plus V. Nope. Nope. Yes. So these 2 are both possibilities, and there's actually a third possibility that's not listed as well, where V is not the first one. So let's say V is in the middle. So another possibility would be something like this. So these are the 3 possibilities we still need to distinguish between. So we know that this case, because the parentals is the most common, we know that these are the 3 possibilities. But now we need to use this other data in order to figure out what is the correct order. And the most important thing then for figuring out the correct order is using the double crossovers. So, and the way you use the double crossovers is, again, we know the double crossover flips the middle gene. So how does this work? So if the order is this, so what do we know that happens? So the original combination is plus VBM. Or PR plus. And we know that the double crossovers are this. So right here, if this was the right order, PRV then BM, then we know that these two combinations would be the same, but we would simply switch the middle one right here. And so if we switch the middle one, what would be produced? Well, this would still be plus, this would become plus, and then this would become BM. So this is not matching what the results are. So we know that V cannot be the gene in the middle. So, this allows us to then exclude, oops, I'm sorry, I got this wrong. This, of course, was supposed to be the situation where V was in the middle. So this all right. So we know that this is not correct because if V was in the middle, we would not produce these gametes. What about this situation right here? What happens if we switch these two genes? So in this case, the double crossover that would be produced would be V plus plus. Then on the other one, it would be plus BM PR. So again, these do not match the result. And then finally, we consider the third case where PR is in the middle. And so if PR is in the middle, then we would switch these two. And as a result, we would have V, PR, BM. And then we'd have plus, and then we would switch this one to plus, and then plus. And so this actually matches the results. So now we know that this is the correct situation. And so we've inferred we've inferred both the parental gametes and now the gene order. And so this just kind of shows that situation right here. So PR is in the middle. And so now we have the single crossover events. So these are the single crossovers right here. So how do these single crossovers create plus plus BM and PRV plus, for example? So right here is that class. So we've drawn this correctly. So V plus BM and plus PR plus, these are the parental gametes. And so if we have a single crossover that occurs between the first and the second gene, then these are the two types of gametes that can be produced. So V, and then we cross over and do PR and plus, or we can do plus, cross over and get the plus and the BM. Or we could have a single crossover event right here between the second and the third gene. And so V plus plus or plus PR BM. And so that's what these different categories are right here, these single crossovers. So these single crossovers just show you, so this just matches this right here. So how do you go about now figuring out the gene distance between the different genes? So now what you need to do is find all of the examples of recombinants between here. So the original combination is this, okay? So if I want to figure out the distance between V and PR, what I need to do is find all of the gametes that have changed this combination. So instead of being V plus, it would now be plus plus or V PR. Okay. So if I go back and look at that, so plus plus VPR and VPR. Okay, so there's 4 different categories here that results in a change in the combination for the first 2 genes. So I simply just need to add these up. 82 plus 79 plus 44 plus 42. And if I do that and I calculate the total distance, I will get a 22.2.3 distance. And then you can do the same. So this is kind of the way you go about doing this. And really, you just need to start working on examples, I think, to really make sure you understand this. So by watching this lecture, I think you should start to get the basic principles of how you do this. But then you really need to work through examples in order to nail this material down. So the activity, there's a large number of activity problems that kind of help you, give you examples to work through. And hopefully this becomes straightforward by doing that. This chapter is one of the most complicated for students, so you really need to spend a lot of time working on this material. And that is the end of Chapter 5.